All right, so I have already uploaded in my website a blank copy of worksheet number 10. So this is what we'll do during the duration of the week. And if we finish early, because I see you are well ahead in the lecture, so I'll try to add some more or to start doing some examples on sections 3.3 and 3.4 if possible. But this is quite a heavy set of topics, especially the first few ones, because here we're supposed to talk about related rates, velocity, and rectilinear motion, and then two other important theorems in calculus, namely Rolle's theorem and the mean value theorem. But I want to focus more on related rates. Side note, most students, yeah, from my experience, this is what most students find the hardest topic in calculus, related rates. Of course, I think all word problems would be difficult because you are not explicitly given a problem for which you can apply those mechanical tools that you should have obtained when we go to these topics. But there's an additional challenge for word problems. That is, you have to analyze the given problem, deduce from it the given information that you can use in solving it. Plus, you have to work out the working equation. And I guess that's the main difficulty in doing related rates problem. So what I'll try to do is that though in this worksheet, there are just five problems in involving related rates. So I hope to go over them in details. And maybe I can also devote the entire time doing this. And if you have some problems, I can some questions about related rates, I can browse through some materials from the textbook. But maybe that's where we will focus. And then hopefully on Wednesday, we can go ahead with the remaining problems in the worksheet. Okay, so for related rates, uh, this is a list of the suggested steps in how to work with related rates problem. Obviously, first, you need to understand the problem. Basically, read the problem, reread the problem until you get the main idea of it. And if necessary, you draw a picture. And I guess for me, it's almost automatic for me when dealing with the related rates problem. I draw a picture. The reason is that number one, it will give me a visual representation of the problem, from which I can clearly see the relationship between the variables, because it's very important that you deduce what would be the relationship between the variables involved in the problem. And number two, it is also a good avenue in which you can define the variables that you will be using, which will aid somebody who will read your work. Because sometimes we tend to use our own set of variables or notations. So having a picture with all information labeled would be very helpful, right? Not only for you, but also for the one who will be grading your work. Okay. And then point of step number one is so that we can proceed to step number two, which is determining a working equation that relates all of the quantities involved in the problem. And sometimes you will have to deal with more than one equation. Sometimes two or more equations will be related to each other. Sometimes they are completely different. So hopefully we'll see a variation of problems later. And that's a crucial part because after having a working equation, this is basically uh, just mechanical things. We do implicit differentiation. Most of the times we do implicit differentiation with respect to the time variable, but later you might encounter some problems wherein you need to differentiate with respect to another variable other than time. But actually, the variable of differentiation is always dictated upon by the problem itself. So you'll see it later when we analyze these problems. And then this is important. After implicitly differentiating both sides of the equation, that's the only time that you are free to substitute all the values given in the problem, right? So it's clear, it's very important that you don't interchange steps three and four. There are some exceptions. I'll mention them briefly later, but the safest way to solve related rates problem is first to do implicit differentiation first. And after performing that, you can now substitute all the given information from the problem. And then lastly, you do some algebraic manipulations in which we solve for the desired quantities or the quantities that is sought for in the problem. Okay. Whenever I answer word problems, any word problems, I usually follow Polia's heuristic. I don't know if you heard of it. Uh, it's a good problem-solving technique. Maybe yeah, which I guess which I learned since elementary grade, and I guess you have already heard of it. Well, this is basically you identify what is being asked in the problem, identify what are the given information. Third, you write the mathematical sentence. Fourth, you do the mathematical operation, and five, you write your conclusion. And though I learned it in the elementary grade, I still find it very helpful in solving problems even up to now in the graduate level. And I'll illustrate to you how to use that. And yeah, I guess that's it. Okay. Now, related rates problem require us to have a working equation, and this working equation relates all the variables given in the problem. Usually, they will be coming from formulas from geometry or from algebra, possibly trigonometry from time to time. But here is a list of some of the basic formulas that might be useful when we deal with related rates problem. So you can start memorizing them. I'm not sure if the working equations will be given during the exam, but it will be very helpful if you memorize at least these basic ones or try to recall these basic ones. Okay, so I guess all of the things I said would be easily understood if we apply it to certain problems. So if you don't have any questions so far, let me try to solve problem number one. Okay. So for problem number one, we have this. A heap of rubbish in the shape of a cube is being compacted into a smaller cube. Given that the volume decreases at the rate of 6 cubic meters per minute, find the rate of change of an edge in meters per minute of the cube when the volume is exactly 64 meters. Okay, first, we draw a picture of the problem. Since I'm not good at drawing three-dimensional objects, I have copy-pasted here a picture of a cube. And if we look at the problem, actually, it looks like we need to consider the volume of the cube. So aside from having a pictorial representation of the problem, I usually use it to define the variable. So I write a V here to denote the volume. And then, of course, when you talk about the volume, you look at the measurement of an edge, right? So actually, the problem specifically mentions it. So I'm just going to label the length of an edge and denote it by the variable s, yeah, the usual variables that we use, okay? And then I'll try to apply Polia's heuristic. Okay, so first, what is being asked in the problem? So if you're going to read the problem, you go to the last sentence and you see that it is asking for the rate of change of an edge, okay? Remember, when we talk about rate of change, derivative should pop out of your mind, right? So the concept of derivatives would be the one used here because it's a rate of change problem, and the rate of change that we are after would be the rate at which the edge changes, right? In meters per minute. So it's the rate of change of an edge, but in the picture I drew, I used the variable s to denote the length of an edge. So I know I'm looking for ds, the derivative of s, right? Because it's the rate at which the side length changes with respect to what variable? Now look at the problem again. It says find the rate of change of an edge in meters per minute. So that means I want to take the rate at which the measurement of an edge changes with respect to time, measured in minutes. So I know that I need to differentiate with respect to time. And actually, this is the reason why I wanted to write derivatives in Leibniz notation, in the ds over dt notation, rather than the s prime notation, though in one-dimension calculus or in calculus 1 and 2, s prime is understood to be the derivative with respect to the independent variable, which in this case is time. But I always find it more informative to use the Leibniz notation because you can treat the numerator to be the changing variable. In this case, the changing variable is s, which is the length of an edge. And the denominator, or the variable in the sort of quote unquote denominator, is the variable with respect to which the change is being measured. So here we are measuring the change with respect to time, and we use t as the usual time variable. So I know that ds over dt represents the rate at which the side length changes with respect to time. Okay. Okay. The rate of change, or derivatives of rate of change, is an instantaneous value. It's the rate of change at a particular moment of time. So we need to identify at what particular moment do we want to take ds over dt. If you go back and read the last sentence of the problem, we were told that we want to find the rate of change when the volume is exactly 64 cubic meters. So we want the instantaneous rate of change when the volume is 64 cubic meters. So I can write here, we need to find ds over dt when, or at the moment, when the volume is exactly 64 cubic meters. Okay, so this is what is asked in the problem. The next step in Polya's heuristic is to identify what are the given facts. So we are given what? We are given, go back to the problem, reread it, and identify sentence by sentence or phrase by phrase what are the given information. So here, look at the first sentence is just a story. The second sentence, given that the volume decreases at the rate of 6 cubic meters per minute. So that's a juicy information for us. It tells us that the rate at which the volume changes. So we know that that should be dv over dt. Again, the beauty of Leibniz notation. dv over dt will remind us that it is the rate at which the volume changes with respect to time, right? And from the problem, it is said that this should be equal to 6. Actually, not just 6, but it should be negative 6. Do you guys realize why it should be negative 6? You can unmute your microphones if you want to answer, or type it in the chat. Okay, thank you, Belurin. Right, it should be negative because the problem says that the volume decreases at the rate of 6 cubic meters per minute. That means the rate of change should be negative so that it will have a decreasing behavior, right? So you need to be very careful, read the problem thoroughly so that you can identify these minute details. These minute but very important details, all right? So given dv over dt, and are there any more information? I guess that's all of it, right? So essentially, the entire word problem is reduced to finding ds over dt when v is equal to 64 given dv over dt equals negative 6. So basically now we have a good idea, or at least a mathematical idea of what the problem is all about, right? Now the next step is to write the mathematical sentence. Basically, this is determining what is the working equation. Well, the working equation should involve most, if not all, of the variables in our statement here. So maybe I should box this one. Okay. So if you look at this box statement here, the working equation should be coming from this statement, or should be coming from all the quantities involved in this statement. Obviously, we have the volume, and we have ds over dt, so that at the back of our minds tells us that we should relate the volume to the side length. But that is easy because if you go back to the basic geometric formulas, this will only remind us of one thing: the formula for the volume of a cube, right? The volume of a cube is equal to s cubed, right? And then a good way to check if we have the right form of the working equation is imagining implicitly differentiating this equation, right? So if we're going to do implicit differentiation, on the left-hand side, we're going to have a dv over dt, which is fine because we know the value of dv over dt. And then on the right-hand side, if you're going to differentiate with respect to t, we will have ds over dt, and that's perfectly fine because ds over dt is what we are looking for. All right. So I guess we have all the derivatives, or actually, when we do the implicit differentiation, we can work with the derivatives that will pop out of that expression. All right. Now we perform the mathematical operation, step number 4 in Pauli's heuristic. Okay, so step number 4, perform the mathematical operation. In this case, that is implicit differentiation. So we differentiate with respect to time because all of the information we got from the problem are all derivatives with respect to time. So when we differentiate with respect to time, we get dv over dt equals, this is something cubed, its derivative is 3 something squared times the derivative of the something with respect to time. All good? And now we're done differentiating. And if you go back to the steps enumerated in the first slide, we can now plug in all the given information, right? Once you are done differentiating, you can now use all the given information from the problem, all right? Now, dv over dt was given to be -6, so I'll plug that in, equals 3. Do we have the value for s? Unfortunately, we don't have the value of s, so we should find a way how to find s. And then ds over dt is the unknown, so we'll just keep it here, okay? Now, this is typical when one of the variables is missing, right? It's fine if you miss one of the variables because chances are we can solve for it using the instantaneous information, right? But we cannot circumvent the lack of a derivative, right? So fortunately here we are just missing the value for s, but all of the derivatives are fine. So that's why I knew this is a good working equation because the only missing thing is s. There are no derivatives missing, right? But how do we find the value of s? We need to go back to the problem and look at what is the particular moment of interest. The particular moment of interest here is when the volume is equal to 64. But remember, the volume is s cubed, right? And since at the particular moment of interest, the volume is 64, we just need to find what is the value of the side length at that particular moment of interest. And I hope you see now the process, because once we are done differentiating, what we get here is an equation at a particular moment of time. In particular, the moment of time that we are interested in finding the rates of change, okay? Now, if I'm going to solve for s here, I simply need to take the cube root of both sides, so I'll get s is equal to 4, right? So at the particular moment of interest, that is when the volume is 64, the side length is equal to 4. So I can plug in 4 here. Because I'm done differentiating, I can plug in any instantaneous value after we do the implicit differentiation. And what's left to be done is to carry out the arithmetic or the algebra to find the unknown quantity. Remember, the unknown quantity here is ds over dt. So I'll just perform the arithmetic. So this would be -6 times 3 times 16. So that's going to be 48 ds over dt. And then I'm solving for ds over dt. That is equal to -6 over 48, or that's -1 over 8. So that's a mathematical solution. But the fifth and final step in Pauli's heuristic is to write a conclusion which will answer the problem in the appropriate context. In most word problems, the appropriate context is the dimensions of the calculated quantities or the units of measure, right? So remember here that all the quantities were given in terms of meters, or all the spatial quantities are given in meters, and the time variable is measured in minutes, or in minutes. So here, I will interpret the answer of -1/8 by saying that, therefore, when the volume is 64, cubic meters, the side length changes at the rate of -1/8. Oops. So this is a side length, so it will just be meter per minute. Okay, but there's I think a more elegant way to answer this. Because I think I usually prefer saying that the side length decreases at the rate of 1/8 meter per minute. Right. So I hope you see the distinction here. When you just say that the side length changes at a certain rate, you should include the sign because that will tell the reader whether it is increasing or decreasing. And I find it often more informative if we just simply say that the side length decreases at the rate of 1/8 meter per minute. We already mentioned that it is decreasing, so that means the rate given should be positive, okay? Because if you say that it decreases at the rate of -1/8 meters, mathematically what comes to mind is that the the side length actually will be increasing, right? So just be careful in how you write your conclusion. Okay, guys. Does that make sense? Any questions or any reactions? Okay, all good? Or still digesting and figuring it out? Mm-hmm. Oh yeah, even that's fine. It's actually hard, especially if it's the first few times that you have encountered related rates problems. So I guess the thing here is to try to practice with as much problems as possible. Try to get your hands dirty by struggling with these problems. But I hope that your takeaway from this class is a general idea on how to proceed with these types of problems. But I guess the most crucial part of solving related rates problem is how to come up with a working equation. Okay, because that's a crucial thing. Because once you get the working equation, almost all that will follow will just be a mechanical application of the things that you have learned in the previous weeks. Right? You do some calculus stuff, or you do some algebraic manipulations, and that's it. But the real challenge here is to come with a working equation. And I guess the easiest way, at least for me, to have a sensible idea of what the working equation is to identify what is being asked in the problem and what are the given facts. All right. So with that, let's try another problem. Okay, just let me know if something is not clear, but I'll try as much as possible to be as detailed, to be very detailed with this, with solving these problems. So that's really why I don't mind spending all of this afternoon with related rates problem. Okay. Right. Problem number 2. A rectangle is inscribed in a circle of radius 5 inches. If the length of the rectangle is decreasing at the rate of 2 inches, how fast is the area changing at the instant when the length is 6 inches? Okay. So I drew here a picture. I have a rectangle that is inscribed. When we say inscribed, that means it is drawn inside of a circle, and the circle and the rectangle will share the same center. So this is the center of the circle that will also serve as the center of the rectangle. Okay. Now, I remember reading something about the length of the rectangle. So I'll just call it L. And of course, traditionally, we call the other side the width, right? So it doesn't matter which one you call the length, which one you call the width. Another thing mentioned in the problem is that the area of the rectangle, is that right? Yeah. So I'll just denote the area by A. So that's the. I hope you see here what I'm doing. I'm writing all the variables inside of the figure so that it makes sense what this variable stand for. Okay. And another information which might help us later is that the radius of the radius of the circle is 5 inches. Remember, the radius is the length of a line segment drawn from the center towards any point in the circle. All right, so that will be helpful later. But these are all the information that we need. Now I'll apply Polias heuristics. What is asked in the problem? If you look at the last sentence, it is asking for how fast is the area changing. So that means we're looking for the rate at which the area is changing. So I'm going to have a dA with respect to what variable. If you look at all the information given in the problem, they are measured, or all of the rates are measured per second. So that tells me that this is a derivative with respect to time. So we need to find the rate at which the area is changing with respect to the time variable t. All right. At what particular moment? When the length is exactly 6 inches. All right. So we need to find dA over dt at the moment when the length is equal to 6. Right. Given what information? Well, let's reread the problem and see what are the given information. First sentence talks about the radius, but that's for the circle, so I don't see the use of it right now. So maybe later we'll go back to that. But the second sentence tells us the length of the rectangle is decreasing at the rate of 2 inches per second. So it's the rate at which the length is decreasing. So that's going to be dl over dt, right? And L is decreasing at the rate of 2 inches per second, so this must be -2. Okay, so dL over dt would be -2. And what else? I guess that's the only information given in the problem, of course, aside from the radius, right? So I'll end it here. Just box this one out. Okay, now I need to know the working equation. Well, the working equation we mentioned should be something that involves all the variables in the mathematical problem that we have formulated here, right? So I have the area and I have the length. So the only basic formula that I can think of right now with these variables involved would be the formula for the area of a rectangle, right? But the area of the rectangle is the length times the width, okay? And then remember what will happen. The next step, if this is the correct form of the working equation, the next step is to take the derivative of both sides with respect to time. And remember that the area, the length, and the width are all functions of time. So if I do differentiation, in the right side, I expect to get a dA over dt, right? Which is fine because that's what we're looking for. And then here, the right side is a product of the length times width. So we will be required to use the product rule. But in using the product rule, we will need the values for dL over dt and dW over dt, right? When we apply the product rule. But if you go back to the mathematical problem that we have posted, there's no mention about dW over dt, right? Remember, it's fine if we are losing the value of the variable. We can be missing L, we can be missing W because there might be a way to deduce them from the given information. But if dW over dt, or if a variable, or actually when a derivative is missing, like dW over dt, there is a very slim chance that we can deduce its value from the given problem. So we as much as possible, will try to avoid using this working equation because this requires us a dw over dt, which is never mentioned in the problem. There could be some exceptions to the rule, but generally finding the value of a derivative is very difficult, if not impossible for some cases. So that's why I'm thinking this might not be the right form of the working equation because of the lack of info about dw over dt. But the working equation should be related to this because this is almost a perfect fit if only we can eliminate the variable w, right? Because once we eliminate the variable w from this working equation, then we're good. We can proceed with differentiating, all right? But let's try if we can really eliminate w. How can we eliminate w? We can eliminate w if we can express w in terms of the other variables present, right? The only other variable present here is L and the area, but of course the area is sort of a standalone variable. So our hopes would be to express the width in terms of the length, right? And we go back to the picture or to the problem and go back to one information that we have set aside from earlier. Remember, we also know that the circle has radius 5. And if that is so, then from here, from the center of the circle, and consequently the center of the rectangle as well, up to a vertex of the rectangle, that should measure 5 units, right? Because that is a radius, okay? And similarly, the line segment coming from the center towards the opposite vertex of the rectangle will also be 5 units long, okay? So in all, the diagonal of the rectangle would be 10 units long, right? And then look at this, I have what? Oops. So here I have a right triangle, right? It's a right triangle, so we know the relation between these values here. We see that the length squared plus the width squared should be equal to the hypotenuse squared. But the hypotenuse is 5 plus 5 is 10, so this would be 10 squared. And then from this equation, I can solve for w in terms of L. I can have w squared equals 100 minus L squared. I take the square root of both sides. But supposedly we have plus or minus over here. But what is w? W is the measure of the width. And we assume that the measure of any real life object would be a positive value. So we just take w to be the positive square root. Okay? Actually, I will write it as 100 minus L squared raised to the 1/2, right? Because I'm expecting to use the power rule later when I differentiate, okay? So now the working equation becomes area equals length times 100 minus L squared raised to the 1/2. So now we got rid of the problem of having to deal with dw over dt, which was never mentioned in the problem. And if you take a look at the right-hand side, it's just it just involves the variable L. So when we do implicit differentiation, we'll only have a dl over dt on the right side, which is fine because we already know what the value of dl over dt is, okay? So I guess we can now proceed to implicit differentiation. So we differentiate both sides with respect to t. So on the left, I'm going to have dA over dt. Here, it's a product. It's a product of L and this power, right? So I need to apply the product rule. I'll copy the first, and I'll differentiate the second factor, which is 1/2 something raised to the negative 1/2 times the derivative of the something, which is negative 2L dl over dt. Okay, remember I need to apply the chain rule twice because inside something to the 1/2 is 100 minus L squared. So I took its derivative and got negative 2L, but L is not exactly t, it's a function of t, so I need to multiply it again by the factor invoked by the chain rule, so I should have a dl over dt. All right? Is that clear, guys? I know I feel I am talking too fast, but I hope it's fine. Just let me know if I'm going very fast here. But where am I? I'm applying the product rule, right? So I need to have a plus. I'll copy the second times the derivative of the first factor, which is dl over dt. Okay. And now we're done differentiating. Okay. Now we're done differentiating, so we can plug in all the known information, right? Go back to our mathematical sentence here. We're looking for dA over dt. So dA over dt stays equals, what is the value of L? L is equal to, L is 6, and dL over dt is negative 2. So I'll just simply plug those in here. So we'll have, again, L is 6 times 1 half. 100 minus 6 squared, so that's going to be 36, raised to the minus 1 half, negative 2 times 6. dl over dt is negative 2 plus 100 minus L is 6, so L squared is 36, raised to the 1 half times negative 2. Okay? So here I just plugged in all the given information, all the information that we deduced from the problem. Okay? And then here's my most hated part, doing the arithmetic. So kindly double check my answers here. I'm going to have here a 3. Then I'll have here a 64, but this is raised to the 1 half, so the square root of 64 is 8, but there's a negative exponent, so this would be 1 over 8. And then I'll have negative 2 times 6, that's negative 12 times negative 2, so that's positive 24. Plus, I know that 64, square root of 64 is 8 times negative 2. Okay? So this would be 9 minus 16. So that's going to be minus 7. Okay? And then we write our conclusion. Therefore, when the length of the rectangle is 6 inches, is it in inches? Yeah. The area decreases at a rate of 7 inches per second. Again, I use the term decreases. I should have a positive value here. You could have also written an alternative conclusion that when the length of the rectangle is 6 inches, the area is changing at the rate of negative 7 inches per second. But sort of that doesn't sound well when talking about measurements, because you're talking about negative 7 inches per second. We are used to talking with these measures with values. Okay, questions? I think you mentioned it is somewhat clear. Do you think I can help you clearing some things up if there are some points of difficulties? Or do you mean it's just you think you might need some practice with these problems? How about the others? Do you guys follow? Yeah, that's one of the disadvantages of holding an online class. It's hard to get a feeling of how students are doing with a particular topic. Mhm. Because in the usual classroom setting, I can discern from students' faces how they find a certain topic. Because you might be silent because you understand everything, but definitely I can see it in your face whether you're getting or not. But online class, that's an impossible task. So, okay, maybe let's do some more practice. Let's try problem three. Okay. So here we have a 5-foot ladder leaning against a wall. So let me try to draw this scenario out. Let's say this is a wall, and then I have a 5-foot ladder. So this is my ladder, and we know that this is 5 feet in length, right? And then let's draw the ground here, right? And then, okay. And then it says here that it is slipping against the wall so that the base moves away from the wall at a rate of 2 feet per second. So that means the base of the ladder is moving away from the wall at a rate of 2 feet per second, right? And since we have a rate of change there, might as well name this or use a variable to denote this length. Let me call it x. You can use your favorite variable, but I'll just stick with x. And then look at the last sentence. How fast will the top of the ladder be moving down? So basically, we're looking for how fast this is going down, right? So that signals me, oh, I should associate a variable with that quantity. So let me call this length, which is basically the distance between the top of the ladder and the ground, to be y. And with this, maybe I can say we really need to find, if you go back to the problem, the rate at which the top of the ladder is moving down. So we're looking for dy over dt at the particular instant when the base is 4 feet from the wall. So if you look at the last phrase in the problem, the base is 4 feet away from the wall. That translates mathematically to x equals 4, right? Given what information? So we are given, if we go back to the problem, the base moves away from the wall at the rate of 2 feet per second. So here we'll have a dx over dt. I know this should involve the number 2, but should it be positive 2 or negative 2? Because these are the tricky things in the problem. Why do you say it should be positive 2 even? You're correct. But why do you think it's positive 2? Okay, one way to determine, right. So Ivan and Tammy, you're both right. Because imagine what happens as time goes by. The x value is increasing because the bottom or how was it called? The base of the ladder is moving away from the wall. So that means as time goes by, x increases, right? So dx over dt is positive. Okay. So this is our mathematical sentence, and hopefully from here, oops, what happened? Hopefully from here we can discern what the working equation is. So here we need to have a working equation that relates what? X and y, right? But what do we have here? We have a right triangle, right? Actually, it's a fair assumption to assume that the wall is a straight wall, or that it is perpendicular to the ground. So here we have a right triangle with x, y, and luckily the hypotenuse. So I guess it screams Pythagorean theorem, right? So I'm thinking that the working equation should be x squared plus y squared equals what? equals the hypotenuse squared. But what is the value of the hypotenuse? The hypotenuse is 5, but Pythagorean says it's 5 squared. So we'll have a 5 squared over here, or 25. All right. But didn't I violated one of the bullets we had earlier? Remember, we were told not to use constant values given in the problem unless we are done doing implicit differentiation. All right. That actually is true for values or measurements that changes through time. But if you are sure that a certain quantity doesn't change through time, meaning it remains constant all throughout the experiment, right? So you can use it right away from the get-go. So for example, in this case, we have the value of the hypotenuse is 5, but that 5 represents the length of the ladder. There's no mention in the problem that the length of the ladder is changing through time, right? The only thing that is happening in this problem is that the top of the ladder is sliding down the wall. So there is no mention that the ladder is losing length, right? So I think it's a fair assumption that 5 remains constant all throughout time. So I can use it from the get-go, right? But if the hypotenuse changes with respect to time, then you are required to keep it as a variable. It's just that in this particular case, the hypotenuse represents the length of the ladder, so we can use its constant value in the working equation from the get-go. Okay, I hope that's clear. And now we examine this candidate for the working equation. Will this work as our working equation? Well, the next step would be to differentiate both sides with respect to time. If we differentiate the right-hand side, no problem with that because it's just a derivative of a constant, so that's fine. The complication here is differentiating the left-hand side. But if we differentiate the right-hand side, here we will have a dx over dt, which is fine. We know its value. If we differentiate the second term, we'll have a dy over dt, which is also fine because we know, because we're looking for dy over dt. So it seems that the derivative of all the variables involved in the working equation are useful for us. So that means this is the appropriate form of the working equation. So I can proceed to the next step, which is differentiating both sides with respect to the time variable. So in this case, we do implicit differentiation with respect to t. So that means here we have a 2x dx over dt plus 2y dy over dt equals 0, right? So look at, I hope you now realize what is the difference of this thing that we're doing right now with the usual implicit differentiation that you learned last week. In last week, you only have 2 variables, right? You only have y and x. So you are not expected to use the chain rule on both of the variables because we are assuming that one of the variables depend on the other one, right? But in this particular working equation, or even in the previous problems that we have considered, we have more than 2 variables involved. In this particular problem, we have x, we have y, and we have the time variable. And we said that that we need to differentiate with respect to time. So x and y should be regarded as dependent variables on time, and hence the chain rule will apply to them. That's why I have a dx over dt here and a dy over dt here. If you will compare this with what you had been doing last time, you will see that they are entirely different. Because from last week, we are taking the derivative of both sides with respect to x. That's why you don't apply chain rule to x. But this time, we are taking the derivative of both sides with respect to t. So the chain rule must be applied to all variables that are not the same as t. That means with respect to x and y, okay? Now we're done differentiating, so I can plug in all the instantaneous values. What are those? We know that x is 4 and dx over dt is 2 at the moment of interest. So I can use these values now. I'll have 2 times 4 times 2 plus 2 times y. I don't know what y is, so I'll just keep it blank. But that's fine. When you're missing a variable, there might be a way on how we can find its instantaneous value, right? dy over dt is the one we're looking for, so it's fine to be there, equals 0. Now we'll try to determine what is the value of y at the particular moment of interest. So you can say at the moment of interest, we know x is equal to 4. And so from the working equation, the Pythagorean theorem, we have 4 squared plus y squared equals 25. That means y squared is equal to 25 minus 16, that's 9. So y is plus or minus 3. But what is y? Y is the distance between the top of the ladder and the ground. So it should be a positive number. So y is equal to 3. We disregard the negative root. Okay? So that means at the particular moment of interest, when x is equal to 4, the corresponding y value is 3. So I'll plug that in here. And then I'll do the arithmetic. So I'll have 16 plus 6 dy over dt equals 0. And then I'll solve for dy over dt. I'm just short on space here. So essentially what you'll get is negative 16 over 6, which is what? Negative 8/3. Okay. One good sanity check to see if you have the right answer, or at least if you have the sign of the right answer, is that you can examine what happens in the problem. Now we have a good feeling that the dy over dt is negative 8/3. But does it make sense that we get a negative value for dy over dt? That would be a good sanity check. So if we go back at the problem, the y represents the distance between the top of the ladder and the ground. Okay, so does it make sense that dy over dt is negative? So imagine what happens as time passes by. If you go back to the problem, or with this illustration, as time goes by, the ladder is sliding down the wall, right? So what happens to y? Y is decreasing through time, right? Because the top of the ladder becomes closer and closer to the ground. So that means at least here we have the right sign for dy over dt, right? So it makes sense. So we can now conclude with more confidence that the answer really is negative 8/3. So you can say that at the moment when, maybe I can just say when the base of the ladder is 4, what is the unit of measure? Feet. It's 4 feet away from the wall. The distance between the top of the ladder and the ground is decreasing at the rate of 8/3 feet per second. All good? Okay. So if you don't have any clarificatory questions or any violent reactions, I'm going to go to problem 4. But again, let me know if that makes sense, because I really typically find it the most difficult part of Calculus 1, answering related rates problem. So I hope you guys have at least get the idea of how to solve related rates problem, and of course, your efficiency in solving such problems will come from experience. So I try more problems during your free time. Okay, let's try problem 4. A spherical snowball is melting in such a manner that its radius is changing at a constant rate, decreasing from 34 centimeters to 18 centimeters in 30 minutes. At what rate, in cubic centimeters per minute, is the volume of the snowball changing at the instant that the radius is 6 centimeters? Okay. All right. So what is being asked in the problem? So we are asked to find at what rate is the volume changing, right? So that means we need to find dV over dt when or at the particular instant that the radius is 6 centimeters, right? That means when r is equal to 6. And what is the given, or what are the given information? I think the only other given information here is that the radius is changing at a constant rate. From 34, it became 18 centimeters in 30 minutes. So that means dr over dt, and the key word here is that the radius is changing at a constant rate. It's a constant rate per minute, so it doesn't matter, or it doesn't depend on the radius itself. So you can use this information that from 34 centimeters, it went down to 18 centimeters in just 30 minutes. But remember that usually rates of change are given per unit of time. Here, the unit of time is minutes, but the decrease in the quantity we observe here happened in a span of 30 minutes, right? So it decreased from 34 to 18 centimeters in 30 minutes. But if you recall, most of the rates are just per minute. So we need to find how many centimeters is lost in the radius per minute. And since we're told that the radius is changing at a constant rate, so that means this is basically 18 minus 34 over 30, right? The numerator gives us the change in the radius. The radius changed from 34 to 18, but that happens in what span of time? It happens in 30 minutes, okay? So that means the rate at which the radius is changing is negative 16 over 30, and that is what? Negative 8 over 15 centimeters or centimeter per minute, okay? And this should really be a negative value because the radius is decreasing. So dr over dt must be negative, okay? So this is our mathematical model or formulation for the problem, okay? Now let's write the working equation, or let's try to deduce the working equation. Well, the working equation should involve the volume and the radius of the sphere, and that's easy. That is just the formula for the volume of the sphere, which is 4/3 pi r cubed, right? But just remember that pi is a constant, so the only variable on the right-hand side is r. So that will require us to have a dr over dt, which is fine. If we differentiate the left with respect to time, that's dv over dt, which is also fine because that's what we're looking for, right? So it looks like this is the right form of the working equation. I can proceed to applying the mathematical operation. In this case, it's implicit differentiation. So we take the derivative of both sides with respect to time. So we'll have dv over dt on the left, and we differentiate the right side with respect to time, keeping in mind that 4/3 pi is a constant, so maybe you can just copy it over, times the derivative of r cubed, which is 3r squared. Chain rule kicks in, so I'll have a dr over dt. Okay. Now we're done differentiating, so I can plug in all the information we already deduced from the problem. dv over dt is the unknown value, so Let's just copy it over. 4/3 pi should be there times 3. And then r, the value of r is 6. Then dr over dt is negative 8 over 15. Well, Balurin, we don't have to differentiate 4/3 pi because 4/3 pi is a constant. Right? So remember, pi is just a constant. It's 3.14159264 and so on. So it's just a constant. Maybe I highlight the wrong part here. This is just a constant. Remember the scalar multiple rule. If you have a constant times a function, its derivative is just a constant, whatever, times the derivative of the function. That's why 4/3 pi is just copied over. Good? Okay. Now, again, this is what I hate, performing the arithmetic. Let's see, 3 will be canceled. And then what? So this would be 36. And then 15, I can cancel a 3 from here. So I'll have a 5. I'll have a 12 left here. So if eventually we'll have 48 times, I'll use a parenthesis for times, 48 times negative 8 pi over 5. And so this is what? Negative 64. Then that's going to be 32, 384 over 5 pi. Okay. Right. Is that correct? I hope I did the arithmetic right. Okay. And does this make sense? It says that the volume changes at the rate of negative 384 over 5 pi cubic cubic centimeters. Does that make sense to be negative? Well, yeah, because the spherical snowball is melting, so the amount of snowball is decreasing throughout time. So we expect dv over dt to be really a negative value. So we can write a conclusion. Therefore, the volume of the snowball is decreasing at the rate of 384 over 5 pi cubic centimeters. Or maybe we can write it this way. What is the unit of time? The unit of time is minutes. At the time, at a particular instant, when its radius is 6 centimeters. Okay. I hope it's getting clearer and clearer as we solve more and more problems. Okay. So let's proceed to problem 5. Unless you want to share something, a question or a reaction. This is the part that I hate. It seems that I am always talking to myself, so I constantly ask if you have some reactions or if you have some questions. Okay, let's try problem 5 if you don't have anything to say. Okay, here a man standing 11 feet from the base of a lamppost casts a shadow 9 feet long. If the man is 6 feet tall and walks away from the lamppost at a speed of 500 feet per minute, at what rate in feet per minute will the length of his shadow be changing? This is a typical textbook problem. I just don't know why it is of interest to measure the length of the shadow of a man. But this is a good This is a good theoretical exercise, though an impractical one. But anyway, let's try to answer this, right? So we have a lamppost here, and then I'm not good at drawing things, so most that you will see will just be stick figures over here. And then we have a man. There he goes. Uh, he is 6 feet tall, and he's walking away from the lamppost at a speed of 500 feet per minute. That means this is the ground. Okay. So let's see. He's 11. Okay, so he's walking here away from the lamppost at a speed of 500 feet per minute. Just rewrite it. Okay. Then of course you have a lamppost here. Okay. And then he is he's casting a shadow, right? And then it looks like I have two different quantities over here. I have this quantity, which represents how far he is from the lamppost, right? So I'll call it X. And then I'll call this S for shadow, the length of the shadow, okay? And then what else? Of course, the lamppost, that should have a constant value. But anyway, here, we want to find what? We want to find the rate at which the length of his shadow is changing. Based on the definition of variables I have in the figure, we will be looking for ds over dt, right? At what particular moment when mhm. Okay, there's no particular moment mentioned here, so I'm guessing that that won't be material. So because here I don't see any particular moment of interest, and that's a signal that we might not even use it, right? So there might be no s or x variable left. So let's just keep it there. Right? So find ds over dt given what? Given what are the given information here? We know that the man is walking away from the lamppost at a speed of 500 feet per minute. So I know there should be a 500 here. That should be equal to some derivative with respect to time. So what does that 500 stands for? It's the rate of change of what with respect to time? Which variable? Uh-huh. Ivan, that's correct. And Tammy, that's also correct. So this is dx over dt. Because remember, in the way I define the variables, x is the distance of the man from the lamppost. And it is said in the problem that the man is walking away from the lamppost at a speed of 500 feet per minute. And 500 should be kept as a positive value because as time passes by, the distance between the man and the shadow increases. So the x would be increasing in time. So dx over dt should be positive. Okay. So I guess that's our working equation. Now I need to determine what is the working equation. So that's a mathematical formulation. Now what is the working equation? Okay. Now it looks like that here we need to relate the variables x and s with each other. Find an equation that involves x and s. But can we what can we use? Well, we assume that the lamppost makes a 90-degree angle with the ground, which is a reasonable assumption. Now, any idea? Well, you might be thinking, oh, there's a right triangle here, so probably will use the Pythagorean theorem again, right? Well, if we're going to use the Pythagorean theorem, that will require us to have an x plus f, that's the base squared, plus the height, that value there, but that's the length of the lamppost. Well, let's just put it there. We don't know exactly how long is the lamppost, but for sure, we might be able. We might be able to find it. So yeah, let's just keep it there. L squared equals, and here's the problem. They should correspond to the hypotenuse, but we don't know how long the hypotenuse is because the hypotenuse actually represents the distance from the top of the lamppost towards the tip of the shadow. And without knowing the length of the lamppost, there's no way that we can know the length of the hypotenuse, right? And chances are that that length of the hypotenuse, even if we will be able to find it, let's call it h, that should vary with respect to time, right? Because unlike the ladder problem that we had before, as time passes by, the length of the hypotenuse changes, right? Because say in the next moment, the man could be here, his height doesn't change, but the hypotenuse or the length of the hypotenuse is clearly changing. So that means h changes through time. When we differentiate with respect to t, we will need a dh over dt, right? And there's no mention about the dh over dt in the problem, so I guess this is a wrong choice of working equation. Yes, Blurin, what's your question?
So I was gonna ask how you got that equation, but I guess you just said it's wrong. So
Yeah. Basically here, it's the Pythagorean theorem. It's the base squared, which is x plus s, quantity squared, plus the length of the lamppost equals the hypotenuse. But as you have seen in this analysis, if I will insist on using the Pythagorean theorem, it will require us to have a dh over dt, but we don't know how fast the hypotenuse is changing. So this is the wrong working equation. That won't work. So another tool that we can use here is, um, do you remember similar triangles? So similar triangles, let's figure out the two similar triangles over here. Well, let's see. Let me just erase the red one. Okay. Okay. Now, where are the two similar triangles? Of course, the first triangle is the big one. Okay. All right. So if this is the big triangle, uh, remember similar triangles? Yeah, congruent, or actually, is it called congruent? No, it's just similar triangles because the ratios of their corresponding sides should be should be equal to each other. So here, if we take the base of the big triangle, what is the base of the big triangle? The base of the big triangle would be x plus s, right? All over the height of the big triangle. What is the height of the big triangle? The height of the big triangle is actually the length of the lamppost. And we don't right now, so I'll just call it L. Okay. And then equals, uh, I'll consider a similar triangle to this, and I'm going to color it green. The similar triangle would be this. That small triangle over there. I don't think you can see it properly. Maybe I can use red. Yeah. So that is the other triangle that is similar to the big one. So what is the base of the smaller triangle? Because remember, we are setting up the equation. We have the base of one of the triangles all over its height, right? So what's the base of the smaller triangle? It's just a smaller triangle. So for the smaller triangle, the base is S. Look at this. That's it. That's S, the length of the shadow. And what is the height? The height is 6 units. 6 feet. Okay. And then, okay. And then let me just rewrite it in another way. I'll multiply both sides by 6L just to get rid of the denominators. So we'll have 6x plus 6s equals SL. Good, right? But to check if we have the right working equation, again, what we do is to imagine what happens when we differentiate. When we differentiate this, we will need dx over dt, which is fine. That is given in the problem. If I'll differentiate the second term, we will have a ds over dt, which is fine because that's what we're looking for. If I go to the right-hand side, I need to differentiate the product of s and l. So remember the product rule. This will require me to have a ds over dt, which is again is fine because that's what we're looking for. But that will require us to have dl over dt, right? Okay. But what can we say about dl over dt? What does that represent? Anybody? What does dl over dt represent? Okay. Yeah, Balurin, that's right. That's the change of length with respect to time. Specifically, it represents the rate at which the height of the lamppost is changing with respect to time, right? But what is that rate? Can you guess what that rate is? What is dl over dt? That's correct, even. It is equal to 0. Precisely because the length of the lamppost is never changing, right? So you see here the dynamics between interpreting the problem and just looking at it from a mathematical point of view. We might have run into a problem if we don't know what dl over dt is. But a careful reading of the problem will tell us, oh, we don't need to worry about dl over dt because that will just be equal to 0 because after all, the length will just be what? The length will just, the length of the lamppost is constant through time, so it doesn't change. So dl over dt would be equal to 0. Okay. Now we can move ahead and differentiate. Okay. So I hope this is fine. So I can leave it here. Or another way to look at it is that L is simply a constant. Maybe that's a better way of saying that, where L is a constant. What is the value of that constant? Maybe it's better to compute that constant here. Though you can go ahead and say that and use that information that we know dl over dt is. But essentially we discovered or we realized that the length should be a constant or L should be constant. But how do we get that? Well, there's a particular moment given in the problem. If you go back to the problem, it says that a man standing 11 feet from the base of a lamppost cast a shadow of 9 feet long. So that means at one particular instant, the triangles look like this. This is 6 feet. And then this is 11. And then this is 9, right? So the man is 11 feet away from the lamppost and cast a shadow 9 feet long. So then we can apply the same principle. We can do the similar triangle thing. Just erase this and obtain the following relation. So the base of the big triangle is 20 all over L, the unknown length of the lamppost, equals the base of the smaller triangle, which is 9, all over the height of the small triangle, which is 6. So this tells us that the length is what? 6/9 times 20. Yeah, just do the algebra there. Okay, guess this is right. And this would be what? Can I cancel things? Uh-huh. Yeah, this will just be 2/3. And so I'll have 40 over 3. So the length, L, is 40 over 3. So you can differentiate right away. At this point, you have two options. Either you differentiate both sides with respect to t, that's fine. But I guess I realized an easier way. Just plug in L equals 40 over 3, which is fine because L doesn't change through time. So I can use that value, 40 over 3. So I'm going to have 6x plus 6s equals 40 over 3s. Okay. Actually, here I can rewrite it as what? 6x plus 6 minus 40 over 3 times s equals 0 before differentiating. But it's your option. You can differentiate right away. And then this is just 6x minus, I guess this would be 22 over 3. S equals 0. Then I differentiate both sides with respect to t. We'll have 6 dx over dt minus 22 over 3 ds over dt equals 0. Okay. And then we plug in the known values from our statement earlier. So we know that dx over dt is 500. So I'll have 6 times 500 minus 22 over 3 ds over dt equals 0. Okay. Okay, are you checking my arithmetic? Hopefully I did it right. And so here we do simple algebra to find ds over dt equals what? Equals 0, 0, 30 negative all over negative 22 over 3, which is basically negative 3,000, or it will be positive now. We'll have positive, so times 3 over 22 over here, right? And then you just need to simplify and then write your conclusion. I hope I did the calculations correctly. But does it make sense to have a positive ds over dt? Because if the man is over here, I'm trying to imagine if this is right. If the man is already here, so that means the shadow he cast would be here. So this length here, at least visually, is longer than this. Right? So that means the length of the shadow is increasing. All right. So I almost used up all of the time we have for today. Do you have any questions? So I leave the completion of the solution to you guys. Though I'll try to upload the annotated worksheets perhaps late tonight or early tomorrow. I'll focus on grading my share of problem 18 from the test that you took last weekend. So it might take me longer to clean this up and upload it in my website. But do you guys have any questions? Okay, if there are no questions, then let's call it a day. You guys have a good day and see you on Wednesday. I just saw Balurin's question. Where would you recommend we practice? If you go to CASA, I think there's a link there to the textbook. There are some good problems in the textbook as far as related rates are concerned. So you can look at those problems, and if you find some difficult ones or you struggled with them, just let me know which problems, and then I can help you with it. And as always, you can drop by the CASA Tutoring Center anytime you need help, especially from 4 to 5 every Tuesday and Thursday. I'm going to be there. So I hope to see you guys there. Okay? So that's it for today. Have a good one, everybody. See you on Wednesday.